morning, everyone. Just to change a little bit the discussion, moving into corrosion. Here we have some study on corrosion of reinforced concrete columns. And if you remember the plenary speaker last night talking about seismic effects. So first, I want to acknowledge my student, Sayal Shrestha, for doing all the work. And part of the talk here will be how we did the corrosion, especially for accelerated bridge construction columns, give you some idea of the details. And then some experimental results. We're in the middle of the program right now. And we did some open seas modeling and some preliminary conclusions. So, of course, everybody knows accelerated bridge construction has advantages. It provides fast project delivery, improved durability, and less interruption to traffic, especially in urban areas, higher safety, and better quality control. So in this research, actually, we have two parts. This is one half of the first part, and we have 4 specimens, of which one is the control. As a column to footing specimen, I will show the details. And the effort was to do a moderate corrosion. The target was about 10% loss in longitudinal reinforcement and considerably more in spiral reinforcement. And we already have something going on with severely corroded specimen. The target is about 25% in the longitudinal and probably 100% in the spiral. And then a similar severely corroded specimen will be repaired before it's subjected to seismic loading. So here is the detail of the specimen. It's an octagonal column, fairly good size, 16 inches, with number 7 bars, 8 of them, and the number 4 spiral, 2 inches. So what happens is the column is constructed separately, and we have here a galvanized duct. And inside the galvanized duct, we have a UHPC that we developed ourselves. And that's how we connect the column. After we connect it, we start the corrosion, accelerated corrosion using a constant current method. Of course, the goal is to determine the steel loss over time. And this shows a picture of how the corrosion is carried out. Basically, 2 feet above the footing, we build this plexiglass container, and we have a 5% sodium chloride solution with a cathode and an anode. And so we are subjecting the column under constant current, and you can see the DC current is translated into the AC into DC voltage. So this goes on for 2 months. That was the process. We didn't crack the column initially. The column was just pure. And you can see on the left-hand side the control specimen, and on the right-hand side, you could see the moderately corroded specimen. So this moderately corroded specimen, I will show you later, had about 10% loss in mass for the vertical longitudinal steel, and about 90% loss for the spiral. Here you can see the corrosion effect in situ with the cracking, of course, and you can see the corrosion byproducts. This is after we did the experiment of the corroded specimen. As you can see, we lost about 10% in area of the longitudinal bars. You can see the bar, of course, had fracture, but this is after the seismic test. But on the right-hand side, you can see also the spiral reinforcement, which in certain sections, pitting corrosion caused about 90% loss in the area. So first, I will talk a little bit about the seismic test for the control specimen. This has no corrosion at all. And you can see the performance is as we expected for a conventional column of this type. About 2% drift. We saw some cracking in the concrete and 3% drift we saw the spalling initiation, which is denoted here on this curve to the right. And then at 8%, we saw cover spalling. And at 9% drift, we saw bar fracture. So one bar fractured in this case. So this was the control. And here you can see for the moderately corroded specimen, we had some initial cracking due to corrosion, of course, at 0% drift before even we started the seismic test. Spalling initiated at about 2%. And then the cover started significantly spalling at 5%. And at 7%, we had the first bar fracture. So you can see here a comparison of the experimental results. We had for the control, which is the blue curve, as I mentioned, the bar fractures at 9% drift. For the moderately corroded, actually we had 2 bars fracture. We had one at 6% drift and one at 7% drift. So definitely you can see also from this graph that we don't get the same drift. The column cannot go to the same excursion, which is significant, of course, for seismic design. So here you can see the hysteretic energy, which is the area under the hysteresis loops. And you can see that up to 7%, the corroded specimen stops, but the control specimen goes up to 9%. So the corroded specimen, you can see that in individual cycles, there's not a lot of difference, but of course, if you accumulate the energy, it's about half. So even 10% loss in longitudinal bar can cause 1/2 the hysteretic energy. So here I'm presenting the modeling now. We use OpenSea's concrete 4 and reinforcing steel. We have done some work earlier for this type of connections with my student Amelie, and we have a plastic hinge length that we heard earlier today about the topic, and it was 8 inches in this case, and we applied an axial load of 6 to 10%. And so this is what was done in the experiment, and you can see here in the plastic hinge, we have a pseudo reinforcing bar. Everywhere else, we have an original reinforcing bar. And the way we do this, we modify the properties to take into account both the corrosion effects as well as the bond effects. So we use for concrete Mander's model, which is very well known. We modified it, of course. This was used for their non-corroded column. For the corroded column, we use a model by Coronelli and Gambarova, 2004, which modifies the properties by reducing the compressive strength of the concrete due to the cracks that form in the concrete from the corrosion process, but also the modification here includes the effects of the bond degradation. So if we were to look at the graphs, here you can see on the left, the unconfined and confined concrete properties. And on the right, you can see the modified material properties due to 10% corrosion, which is the green curve, and 25% corrosion. This is kind of a predictive model for our next test. We're still preparing. And you can see then for the confined is the solid line, the degradation, and for the unconfined is the dotted line. Similarly, for the steel, we use Mander's model, and that steel also was modified for corrosion. For this, we used a model to change the properties of the steel by Yuan et al., where basically the yield strength, the ultimate strength, and strain are modified so that we can get modified properties to represent the corrosion percentage C. What does it do to these properties? So all the properties, the elongation and the strain are changed. And I will show here the graph. So on the left, you see the material property of the steel. And on the right, you see if we reduce the property for 10% corrosion is the green curve. And for 25% corrosion is the red curve. In addition to that, we use a bone slip property because of the type of construction that we did with accelerated construction. And we used the model by Professor Saidi and Tazar, where it's the bone slip in the plastic hinge zone. So it was incorporated in the model using bar slip springs. And you can see the effect of this. On the left side, you can see the stress strain curve without bone slip. That's the solid line. And including bone slip is the blue line. And on the right side, you see the same thing, but for green is the 10% corrosion, and for red is the 25% corrosion. So in addition, we have, of course, a very commonly known low cycle fatigue model, because low cycle fatigue is what causes these bars to fracture when we do the cyclic loading. And in addition to all this, we also have here fatigue model and also buckling model as well. So in the buckling, we have the model by Gomez and Appleton, which accounts for inelastic buckling of the reinforcement and the behavior of the longitudinal steel, considering the slenderness ratio of the reinforcement. So here you can see the comparison for the numerical model for the control specimen. You can see the experiment is the black curve, and the model is the blue curve. It's not perfect, but it represents, we believe, the behavior well. There are some peaks in the experiment that the model cannot capture, but it does capture significant things like the stiffness, the energy, and also the cycle at which the bar fractures. So if the bar fractures on the 16th cycle in the experiment, the model also captures it, as you can see by the two triangles in the same cycle. Now, here is the model for the corroded, moderately corroded specimen. And you can see that it predicts also pretty well, both the strength, the stiffness, and the hysteretic energy. And as well, it predicts the two bars fractured. So this model predicts the two fractures in the same cycle as when the bars fractured after the corrosion. So time is up. As a preliminary conclusion, and we're not done with these 4 tests yet, the control specimen still fracture occurring the 9% drift ratio at a load that we predicted well from analysis. The moderate corroded specimen didn't lose so much lateral force, only 12%, and actually only 4% up to that 7% drift ratio. However, it did lose the corroded specimen from 9%, it went down to 7%. And we also saw some buckling of longitudinal bars. And the corroded specimen ductility was a little bit less, 6 instead of 6.9. But of course, the hysteretic energy was significantly reduced, about half of the control specimen. This is the cumulative energy. And our model, we believe, is competent enough to, at least for now, for the control and moderately corroded specimen to capture all the effects of slip, fatigue, buckling behavior, and even the corrosion effects as well. So I want to acknowledge Tri-Durally and Geneva Rock and the UDF Department of Transportation. And here are the reference that we used in this presentation. And I want to thank you and take some questions. Yes.
A question regarding the analysis. How do you account for the joint sets for the corroded situation? Because it's going to affect the vision of the state.
Right. So in this model, we actually don't look at the joint at all. We assume the footing is fixed, and the only damage happens in the plastic hinge. And the way we attack the corrosion is through reducing the properties of the concrete and the reinforcing steel. So that's how we did it. Now, Of course, now that with the presentation that we saw this morning, you're wondering, are you trying to make this even more resilient? So our next 4 tests, we are going to use post-tensioning in the columns for recentering. And we'll kind of repeat the same process, 1 control specimen, 1 moderately corroded and 2 severely corroded. One of them will be just tested as is, and the other will be retrofitted with composites. If you're interested on how we're going to retrofit it, we have a method that we actually believe is very robust. It's called the donut method. But anyway, it's a composite donut that has headed bars in it and grout. And we've seen this. We've actually separated the column completely from the footing. We're able to reinstall it, almost plant it back with the headed bars and the carbon fiber shell and grout inside. And we have published paper on that. If you're interested, I'll be sharing it with you. Yes.
Yeah, I'm serving the corrosion. I'm serving the corrosion at the protocol learning system. I'm just curious, like that. So if the because sometimes corrosion happens very localized patient. With this accelerated protocol, to be able to consider these.
So that's why we have the bath, the water bath in the lower end where the plastic hinge is. So we want to induce most of the damage in that region. But you're right, there are localized effects. And of course, that's part of the corrosion. And we saw that in the spiral. We had localized pitting. But that's what happens in real life, we believe.
What about this session, and we'll have a 10-minute break. Yeah, then we discuss it.